All right, I'm going to try and finish the rest of this test review now. I'm going to try and see if we can get all 31 through 43 on the rest of this video here. Solve 1 over 256 equals 256 to the 3x minus 2 power. First thing you got to realize is that you can rewrite this fraction as 256 to the negative 1 power. And when the bases are the same, they're both 256, you can set the exponents equal to each other. So we can do negative 1 equals 3x minus 2. Then you'd add 2 to both sides to get 1 equals 3x. Divide by 3 to get x equals 1 over 3, which is the answer to number 31. And then number 32, write the equation in logarithmic form. 13 to the third power equals 2,197. Remember the rule here. If you have y equals b to the x, you can rewrite that as log to the base b of y equals x. So we'll start with the log base 13. And it's going to equal, or sorry, log base 13 2197. I'm just using these two equations here, and that equals what's left over. In this case, that's 3. So that's how you write it in logarithmic form on number 32 there. Let's talk about number 33. Number 33 says write the given equation in exponential form. So that's the same rules. Y equals b to the x, and then log base b of y equals x. So it's in logarithmic form, so I'm going to write it in exponential form. Start with the base. The base of the logarithm is 6. To the negative 6th power equals 1 over 46,656. And that's how you'd rewrite number 33. It's not much work to show there, obviously. Number 34, the function f of x equals 40 times 0.904 to the x power, where x is time in years, models a declining lemming population. How many lemmings will there be in 6 years? Well, we can just plug a 6 into the function there, so we're finding f of 6, which is 40 times 0.904 to the 6th power. And at this point, we're going to use the calculator. And I'm going to type in 40 times 0.0904 to the 6th power. So after 6 years, how many will remain? 34. There are, and of course I mistyped that. That should be 0.904. So after 6 years, there's around 22 lemmings left, according to my calculations here. Obviously, you can't have 0.83 of a lemming, so there's around 22. 35. An antibiotic is introduced into a colony of 15,000 bacteria during a lab experiment. The function below can be used to model the number of bacteria in the colony after m minutes. Which value is the closest to the amount of time needed for the population of the colony to drop to 9,000 bacteria? So that means that we're going to have 9,000 left. So I'm going to set that 9,000 equal to 15,000 to the times to the m over 9 power. So the first step here to solve this is you'll want to divide both sides by 15,000. So I'm just going to do 9,000 divided by 15,000, and that's 0.6. So we've got 0.6 equals 0.816 to the m over 9 power. So we can use our change of base rules to write this as a logarithm. Log base 0.816 0.6 equals m over 9. So to get the m by itself, to get the number of minutes, we're going to multiply both sides by 9. But I also need to change the base here so I can type in the calculator. So m equals 9 times log 0.6 divided by log 0.816. And that's what I'm going to type in the calculator here. So let's see here. 9 times log of 0.6 divided by log of 0.816. So on 35, we're getting, let's see here, 816, 22.6 just about, if I'm doing this right. So I got 22.6 minutes for number 35 there. 22.6. 36. Describe the transformation that results in the graph of g. We've got f of x equals log x and 2 log x minus 6. So I see two transformations. One of them has to do with the 2. That's a vertical stretch by a factor of 2. And that minus 6 shifts it down 6 units. 37. Write a compound interest function to model the following situation, then find the balance after the given number of years. 14,300 invested in a rate of 4% compounded annually for 5 years. So the function, I guess we're using an A, would be that 14,300, and it's compounded annually, so that's 4 plus 0.04 over 1, the 1 times t, in this case it's 5. So we would just need to type this all in the calculator to get and see what it spits out. So let's see, 14,300 times 1 plus 0.04 divided by 1 to the 1 times 5 power. And that spits out for 37, about $17,000, 398, and about 13 cents. Now I round that down to 13 cents because the bank, they always round in their favor, so you can round that up to 14 cents. What is the asymptote for this equation? Log base 2 of x minus 2. Well, logarithms have an asymptote at x equals something. And generally, it's x equals 0 for the parent function, but this thing has been shifted to the right 2 units. So it's not, the asymptote's not at x equals 2, or sorry, at x equals 0. It's at x equals 2. That's the place that it never touches. 39, moving right along. Evaluate the logarithm. This is calculator work. Log of 1 over 64 divided by the log of 4. Type that in and see what the answer is for number 39. And I'm getting -3 for 39. And let's solve. 9 to the power of 10n minus 6 equals 1 over 6,561. Remember, we want the bases to be the same. Power of 9. So powers of 9, let's see, what was that number we're looking at? 6,561. That's 9 to the 4th power. So I'm going to rewrite this as 9 to the 10n minus 6 equals 9 to the -4th power, because it's 1 over 6,561. Now let's set those exponents equal to each other. 10n minus 6 equals -4. Add the 6, divide by 10. You get n equals 1 over 5 when you reduce it to 2, from 2 divided by 10. 41. Suppose you invest $400 at an annual interest rate of 2.5% compounded continuously. How much will you have in the account after 2 years? That's the equation A equals P e to the RT. And the A is what we're trying to find. P is the principal. E is the constant. The rate is 0.025. Just take that 2.5%, divide by 100. And the T is the time, so we're going to multiply it by 2. Let's see what it comes out to be here. 400 e to the power of 0.025 times 2 is just about $420. And that should be 50 cents because the bank's going to round that down. It never rounds in your favor. Evaluate. Last one we're going to do here. Evaluate the expression. This is calculator work. Log 343. It's just your change of base formula divided by log 7. Log 343 divided by log 7. That's 3. For these graphs here, I guess we should talk about these. The first step is to identify the parent function, which is going to be g here. G is y equals log base 2 of x. And the reason I know that is because it has this point here and this point here. I know that the logarithm passes at 1, 0, and that the next point is always whatever the base is, wherever it's. So this is at 4, 2. It's also at 2, 1. That's the one I was looking for. 2, 1. Log base 2 has its first point that we can write is 1, 0, and then the next one is 2, 1. Now I'm not going to do all of these for you because I'm out of time, but I will identify the next parent function is y equals 2 to the power of x. And I know that because I've got this point, the y-intercept 0, 1, and the point 2, 1. Now you can figure out the rest of these just by doing transformations of that parent function. So like this one is the same as that, it's just been shifted to the left 2. So this is just log base 2 of x plus 2. And I'm out of time, so I can't do all of these. I apologize, but you can figure out the rest of these by doing the transformations of these two parent functions. All right, thanks for watching. Good luck.